Right now, as you listen to this, somewhere in the observable universe, a star is dying. Not quietly, not gracefully, not the way our sun will eventually puff out its outer layers and settle into a gentle retirement as a white dwarf. No, this star is dying violently, catastrophically, in a way that, for a few fleeting seconds, makes it the single brightest object in the entire cosmos, brighter than every other star in every other galaxy combined. And here is what makes that truly terrifying. In those few seconds of destruction, that dying star releases more energy than our sun will produce over the course of its entire 10 billion year lifetime. Not a fraction of that energy, not a percentage. More. All of it compressed into a burst of gamma radiation so intense that it can be detected by instruments orbiting our little planet from literally the other side of the observable universe. We call these events gamma ray bursts, and they are, without exaggeration, the most powerful explosions in the known universe since the Big Bang itself. On October 9th, 2022, one of these bursts slammed into our solar system after traveling through empty space for 1.9 billion years. It was so absurdly bright that it blinded nearly every gamma ray satellite in orbit. Instruments specifically designed to observe the most violent events the cosmos has to offer were saturated, maxed out, unable to fully measure what had just happened. Lightning detectors in India registered disturbances in our ionosphere. The very atmosphere of our planet shuddered. Astronomers gave this event a nickname. They called it the boat, the brightest of all time. Statistical analysis later showed that an event this bright should only happen roughly once every 10,000 years. We just happened to be looking when it went off. Eric Burns, an astrophysicist at Louisiana State University, who helped lead the analysis, described the energy involved in blunt terms. If you took our entire sun, all 864,000 miles of diameter, all 600 million tons of hydrogen being fused every single second, all the light and heat it will ever produce across its entire lifespan, and you somehow converted the whole thing into pure energy, it still would not match this single gamma ray burst. Just let that comparison sit for a second. The sun, that impossibly massive thermonuclear furnace, the thing that can sunburn your skin from 93 million miles away. All of its energy, past, present, and future, not enough. And here is the part that really keeps astrophysicists up at night. The universe produces one of these events roughly every single day. Somewhere, in some galaxy billions of light years away, something unimaginably violent happens. And for a handful of seconds, that one spot outshines everything. This is the story of how we discovered these cosmic detonations, how we stumbled upon them during the Cold War while hunting for nuclear bombs, how they baffled the entire field of astrophysics for 30 years, how we eventually figured out what causes them, and how the answers turned out to be even more incredible than the mystery. So settle in, get comfortable, and let your mind wander to the darkest, most violent corners of the cosmos, because this story is a long one. And it starts, of all places, with a nuclear arms treaty. The year was 1963, and the world was holding its breath. The United States and the Soviet Union had spent nearly 2 decades locked in a contest of mutual destruction, each side building arsenals capable of ending civilization many times over. The dread of nuclear war permeated every layer of society. American schoolchildren practiced duck-and-cover drills beneath their wooden desks. Families excavated shelters in their backyards and stocked them with canned goods. The doomsday clock, that famous symbolic timepiece maintained by atomic scientists, sat perilously close to midnight. But in 1963, something shifted. Just 1 year after the Cuban Missile Crisis had brought the world to the very brink of nuclear exchange, the United States, the Soviet Union, and the United Kingdom signed the Partial Test Ban Treaty. It was a landmark agreement that forbade nuclear weapons testing in the atmosphere, in outer space, and underwater. Underground detonations were still permitted, but the era of mushroom clouds blooming over Pacific atolls and Arctic tundra was supposed to be finished. There was, however, a problem, and the problem was trust. Well, the Americans did not trust the Soviets to honor the agreement, and in fairness, the Soviets probably harbored similar suspicions about the Americans. Verification was essential. The United States military needed a way to confirm, independently and without relying on anybody's good word, that nobody was setting off nuclear weapons where they were not supposed to. They needed sensors in orbit, and not just any sensors. They needed instruments sensitive enough to catch the distinctive flash of a nuclear explosion from tens of thousands of miles away, even if someone tried to hide one in deep space or behind the far side of the moon. And so the Vela program was born. The name came from the Spanish verb velar, meaning to watch or to keep vigil. It was an apt name for what these satellites would do. Beginning in October 1963, just days after the treaty officially took effect, the United States Air Force started launching Vela satellites into orbit, always in pairs, positioned on opposite sides of a high circular orbit, roughly 65,000 miles above the Earth's surface. That altitude, far above the Van Allen radiation belts, gave them a clear, unobstructed view of the entire planet and the surrounding space. Each satellite carried a suite of detectors, gamma-ray sensors, X-ray counters, neutron detectors, and optical flash instruments. Together, they constituted a comprehensive toolkit for sniffing out the telltale signatures of a clandestine nuclear detonation. For years, the Vela satellites watched in silence. And for years, the Soviets appeared to be keeping their end of the bargain. No unauthorized nuclear flashes appeared. The satellites dutifully circled the Earth, quiet sentinels performing their classified role in a tense geopolitical standoff. Then, on July 2nd, 1967, at precisely 14 hours, 19 minutes Universal Time, Vela 3 and Vela 4 simultaneously detected something unusual. A burst of gamma radiation. It was intense, it was brief, and it matched absolutely nothing in the catalog of known nuclear weapon signatures. See, a nuclear detonation produces a very specific gamma-ray profile. There is an incredibly intense initial spike, lasting less than a millionth of a second, followed by a predictable, gradual decline as radioactive isotopes decay. Physicists had studied these signatures exhaustively. They knew what a bomb looked like from orbit. The signal that arrived that July afternoon looked nothing like a bomb. There was no sharp initial spike, no smooth exponential fade-out. Instead, The data showed two distinct humps in intensity, separated by a brief dip, and then a long, slow tail that faded into the background noise. At the Los Alamos Scientific Laboratory in New Mexico, a physicist named Ray Klebesadel was responsible for reviewing the gamma-ray data streaming down from the Vela constellation. When he examined this particular signal, he recognized immediately that it did not match a nuclear test. As he later recounted, the non-nuclear nature of the event was apparent from the very first look at the data. But if it was not a bomb, then what was it? It was not coming from the sun. No solar flare had been recorded that day. It was not a known supernova or any previously catalogued astronomical event. Klebesadel and his colleague, Roy Olson, noted the anomaly, filed the data, and continued their primary mission of treaty verification. It was unusual, certainly, but not deemed urgent enough to warrant immediate investigation, except the signals kept appearing. As newer, more capable Vela satellites were launched throughout the late 1960s and early 1970s, the team at Los Alamos continued to detect these puzzling gamma-ray flashes. Vela 5, launched in May 1969, had significantly improved time resolution, allowing the shape of each burst to be measured with greater precision. Every new detection confirmed the same basic picture: brief, intense flashes of gamma radiation, lasting anywhere from a fraction of a second to roughly a minute, coming from seemingly random directions at seemingly random times. The launch of the Vela 6 satellite pair in April 1970 provided a crucial new capability. With multiple satellites widely separated in orbit, the tiny differences in arrival times of the gamma-ray photons at each detector could be used to triangulate the approximate direction of the source in the sky. The technique was imprecise, but it was enough to start ruling things out. And what the triangulation revealed was remarkable. These bursts were not concentrated along the plane of the Milky Way. They were not clustered around the sun, the planets, or any known nearby astronomical object. They appeared to come from everywhere, uniformly scattered across the sky, as if the entire universe were flickering with invisible explosions. Whatever was producing these signals, it was not anything in our solar system, and it was probably not anything in our immediate galactic neighborhood. In 1973, after 6 years of accumulating data and carefully ruling out instrumental artifacts, atmospheric effects, and every other mundane explanation they could think of, Klebesadel and his colleagues Ian Strong and Roy Olson finally published their results. The paper appeared in the Astrophysical Journal under the deliberately understated title, Observations of Gamma-ray Bursts of Cosmic Origin. In it, they described 16 distinct burst events detected between 1969 and 1972, and they concluded, with careful scientific restraint, that these events were genuinely cosmic in origin, coming from somewhere out in the deep universe. And contrary to what is sometimes reported, the Vela data was never classified. The delay in publication was not the result of government secrecy. It was the result of scientific caution. These were meticulous researchers, and they wanted to be absolutely certain of their claims before presenting them to the world. When the paper finally reached the broader astronomical community, it landed like a bomb of a different sort entirely. Within months, theorists around the globe were scrambling to explain what could possibly produce such brief, intense flashes of the highest energy form of electromagnetic radiation. Known to physics, a new cosmic mystery had been announced, and the race to solve it would consume the better part of 3 decades. What followed the plebiscital paper was, frankly, one of the most gloriously chaotic periods in the history of modern astrophysics. Gamma ray bursts were everywhere in the data, and absolutely nowhere in terms of understanding. They arrived without warning, flared briefly, and then vanished without a trace. There were no visible counterparts, no X-ray glows that lingered, no radio signals that could be followed up. They came, they burned, and they left nothing behind except a few seconds of data on a detector readout. It was as if someone was setting off the brightest flashbulbs in the universe, and then immediately hiding. Naturally, this drove theorists absolutely wild. By the early 1990s, more than 100 different hypotheses had been proposed to explain gamma ray bursts. 100. That number alone should give you a sense of just how deeply confused the field was. When there are 100 competing explanations for something, what that really means is that nobody has any idea what is going on. The proposals ran the gamut from reasonable to deeply exotic. Some scientists suggested that the bursts came from neutron stars in our own galaxy, perhaps produced by magnetic reconnection events on the surfaces of highly magnetized neutron stars called magnetars. Others proposed collisions between comets and neutron stars. Still others invoked asteroid impacts, flares from nearby stars, or the evaporation of miniature black holes predicted by Stephen Hawking's theoretical work. And at the more speculative end of the spectrum, a few researchers even suggested that gamma ray bursts might be the signatures of extraordinarily advanced extraterrestrial civilizations. The fundamental problem, the thing that made all of this guesswork instead of science, was distance. Nobody could determine how far away a gamma ray burst was, and without distance, everything else was just speculation. Consider the analogy. If you see a light in the distance at night, you cannot tell whether it is a candle 100 feet away or a searchlight 10 miles away. They can look identical from your vantage point. Gamma ray bursts had the same problem. If they were nearby, within a few hundred light years, then they could be relatively modest events, perhaps comparable to the energy of a large solar flare. But if they were far away, at cosmological distances of billions of light years, then the energies involved would be staggering beyond comprehension. And the gamma ray detectors of the 1970s and 1980s, while good enough to detect the bursts, were maddeningly imprecise at pinpointing their locations on the sky. The typical error box from an early interplanetary network detection covered several degrees, an area containing millions of stars and thousands of galaxies. Finding the source of a gamma ray burst in that haystack was essentially impossible. And then, in 1991, NASA launched a new observatory that would change everything. Well, almost everything. The Compton Gamma Ray Observatory was one of NASA's 4 great observatories, an ambitious fleet of space telescopes, each designed to observe the universe in a different wavelength of light. The Compton Observatory's domain was high-energy gamma radiation, and among its instruments was one specifically built for the gamma-ray burst problem. BATSE, the Burst and Transient Source Experiment. BATSE was a beautiful piece of engineering. It consisted of 8 detector modules positioned at the corners of the observatory spacecraft, giving it near-complete coverage of the sky. When a gamma-ray burst went off anywhere above the Earth's horizon, BATSE would catch it, record its intensity profile, measure its spectrum, and determine its approximate direction. Over the course of its 9-year operational lifetime, BATSE detected 27 gamma-ray bursts, an enormous catalog that dwarfed everything that had come before. And when astronomers plotted the positions of all 27 bursts on a map of the sky, the result was stunning. They were distributed perfectly uniformly, perfectly isotropically in the technical jargon. The bursts came from every direction with no preference whatsoever. There was no clustering along the band of the Milky Way, which is where you would expect to see them if they came from objects in our galaxy. There was no concentration toward the galactic center, no hot spots, no cold spots, just a completely even, random scattering across the celestial sphere, like salt scattered uniformly on a dark table. This was, extremely inconvenient for the most popular theory of the time. The prevailing idea in the 1980s and early 1990s was that gamma-ray bursts originated on neutron stars within the Milky Way galaxy. If that were the case, the distribution on the sky should have reflected the shape of our galaxy. More bursts along the galactic plane, more bursts toward the center, fewer bursts at high galactic latitudes. That is the pattern shown by virtually every other known population of galactic objects. Pulsars show it. X-ray binaries show it. Supernova remnants show it. But gamma-ray bursts did not. The BATSE data left only 2 credible interpretations. Either the sources were extremely local, perhaps confined to the Oort cloud surrounding our solar system, where the spherical geometry would naturally produce an isotropic distribution regardless of galactic structure, or the sources were extremely distant at cosmological distances, where the large-scale universe itself is isotropic. If the bursts were cosmological, the energy implications were staggering. A burst visible from billions of light years away would need to be releasing something in the neighborhood of 10 to the 51st through 10 to the 54th ergs of energy. To put that in perspective, the total energy output of our sun over its entire main sequence lifetime is roughly 10 to the 51st ergs. The most luminous gamma-ray bursts, if they were truly at cosmological distances, would be releasing the sun's entire lifetime energy output in a few seconds. Some researchers found this number so extreme that they considered it a reductio ad absurdum, a proof by absurdity that the cosmological interpretation must be wrong. The tension between these 2 camps reached a dramatic public climax in April 1995, when the astrophysics community staged a formal debate on the subject, consciously modeled after the famous Great Debate of 1920, in which Harlow Shapley and Heber Curtis had argued over whether spiral nebulae were part of our galaxy or separate island universes. This modern version was held at the Smithsonian's National Museum of Natural History in Washington, D.C. On one side stood Bowden/Pachinski/Paksinski of Princeton University, who argued passionately that gamma ray bursts were cosmological, occurring in distant galaxies across the observable universe. His principal weapon was the BATSE data itself. That perfectly isotropic distribution, he insisted, was the unmistakable fingerprint of a cosmological population. Nothing in our galaxy could produce it without fine-tuning that bordered on conspiracy. On the other side stood Donald Lamb of the University of Chicago, who defended the galactic model. Lamb proposed that the bursts came from neutron stars in an enormously extended galactic halo. A vast, roughly spherical cloud of objects surrounding the Milky Way, large enough to make the distribution appear isotropic from our position near the center. It was a riveting scientific spectacle. Two brilliant minds, armed with data and conviction, slugging it out over the fundamental nature of the most mysterious objects in the sky. But neither could land the decisive blow. What they needed desperately was not more theory, but a single piece of observational data. An actual measurement of the distance to a gamma ray burst. The stalemate would persist for 2 more agonizing years, and then, in 1997, everything finally broke open. On February 28, 1997, at roughly 2:58 in the morning Universal Time, a gamma ray burst went off. In itself, this was not unusual. Gamma ray bursts happened all the time, but this particular burst, cataloged as GRB 970,228, would become one of the most important astronomical events of the 20th century, because for the first time in the 30-year history of gamma ray burst science, astronomers were actually able to follow up. The hero of this moment was an Italian-Dutch satellite called Beppo-SAX. Beppo-SAX, named after the Italian physicist Giuseppe Beppo Occhialini, had been launched in April 1996 and was equipped with a combination of wide-field gamma-ray cameras and narrow-field X-ray telescopes. This combination was the key. When Beppo-SAX detected a gamma-ray burst with its wide-field instruments, it could rapidly slew its more precise X-ray telescopes to the same region of sky and pinpoint the location with far greater accuracy than any previous gamma-ray satellite, where BATSE could only localize a burst to within a few degrees. Beppo-SAX could narrow it down to a few arc minutes. A tiny patch of sky small enough for ground-based optical telescopes to meaningfully search. Within 8 hours of GRB 970,228 going off, Beppo-SAX had identified a fading X-ray source at the burst location. This was already unprecedented. Nobody had ever seen the X-ray aftermath of a gamma ray burst before. But the real breakthrough came when optical telescopes on the ground pointed at the same spot and found something even more remarkable: a faint, fading optical point of light right where the burst had occurred. It was the first ever afterglow of a gamma ray burst. The afterglow is, in a sense, the smoking gun that the burst leaves behind, while the gamma ray burst itself is blindingly bright but vanishingly brief. The afterglow is a much longer, slower fade in lower energy light. X-rays, then visible light, then infrared, then radio waves, produced as the blast wave from the explosion plows into the surrounding material. Finding the afterglow meant astronomers could finally do something they had dreamed about for 3 decades: They could determine where a burst happened, and more importantly, they could figure out how far away it was. The optical afterglow of GRB 970,228 was observed by the William Herschel telescope in the Canary Islands and other instruments around the world. And when the images were analyzed, scientists noticed something critical. The fading point of light was not sitting in empty space. It appeared to be nestled within a faint, fuzzy smudge of light, a galaxy. A distant, faint galaxy. If the burst was genuinely associated with that galaxy, then it was not in our Milky Way. It was not in the Oort cloud. It was not on a neutron star a few hundred light years from Earth. It was extragalactic, cosmological, billions of light years away. But the definitive proof came a few months later, on May 8, 1997, with another burst. GRB 970,508. This time, the follow-up was even faster and more coordinated. Beppo SAX localized the burst. Ground-based telescopes found the optical afterglow. And then a spectrograph on the Keck telescope in Hawaii, one of the most powerful telescopes ever built, was trained on the fading light. The spectrum revealed absorption lines from iron and magnesium at a redshift of 0.835. In plain language, that meant the light from this gamma-ray burst had been stretched by the expansion of the universe to a degree that placed its origin roughly 6 billion light years from Earth. 6 billion light years. Let that distance sink in. Light from this explosion had been traveling across the expanding universe since a time when our own solar system did not yet exist. The sun had not yet formed. The Earth was still just a diffuse cloud of dust and gas orbiting around nothing. And all that time, this light had been hurtling through the void, spanning a distance so vast that it defies meaningful analogy. Paksinski had been right. Gamma-ray bursts were cosmological. They were the most distant, most energetic explosions in the observable universe. The galactic models were dead. But proving the cosmological distance also meant confronting those eye-watering energy numbers head-on. If a gamma-ray burst at a distance of 6 billion light-years could still be detected by satellites in Earth orbit, the total energy released had to be immense. Early estimates calculated under the assumption that the burst radiated equally in all directions, what physicists call isotropic emission, suggested outputs on the order of 10 to the 53rd ergs. That is a number so large that it strains the imagination. It is roughly the amount of energy you would get if you could take the entire mass of the sun and convert it all into pure energy via Einstein's famous equation, E equals mc squared, in a few seconds. And those turned out to be overestimates, as we would later learn. But not by as much as you might hope. The discovery of afterglows transformed gamma-ray burst science essentially overnight. What had been a field plagued by frustration and speculation became one of the most data-rich, rapidly evolving areas of astrophysics. Within a few years, dozens of afterglows had been detected. Distances had been measured for many of them, and the host galaxies in which they occurred were being studied in detail. The 30-year mystery was not fully solved, not yet, but the dam had broken, and the answers were finally starting to pour through. Let us, then, take a step back from the story of discovery and talk about what gamma rays actually are, because understanding the nature of this radiation is essential to understanding why gamma ray bursts are so extraordinary and why they were so maddeningly difficult to study for so long. With the distance question settled, astronomers could finally focus on the real puzzle: the origin of gamma ray bursts. And the first critical clue had actually been hiding in the data all along. As far back as the first BATSE catalog in the early 1990s, researchers had noticed something curious about the duration of gamma ray bursts. When you measured how long each burst lasted, using a metric called T90, the time during which 90% of the burst's total energy is received, and then plotted all those durations on a histogram, you didn't get a single smooth bell curve. You got two humps, two distinct populations separated at roughly the 2-second mark. There were short bursts lasting less than about 2 seconds, often just a few hundred milliseconds, and there were long bursts lasting anywhere from a few seconds to several minutes, sometimes even longer. The two populations also differed in their spectra. The short bursts tended to have harder, higher energy radiation, while the long bursts were somewhat softer. This bimodal distribution was a powerful hint that gamma ray bursts weren't a single phenomenon with a single cause. There appeared to be two fundamentally different types of cosmic catastrophe at work, each producing its own distinctive flash of gamma rays. Understanding each type would require decades of additional observation and theoretical work. But by the early 2000s, the broad outlines had become clear. And the story of each type is, in its own way, one of the most dramatic in all of astrophysics. Let's start with the long bursts, because they involve the most spectacular death scene in the universe. To understand a long gamma ray burst, you have to understand the life cycle of a very particular kind of star, not an ordinary star like our sun, which will live a quiet 10 billion years before gently puffing off its outer layers and fading into a white dwarf. No, we're talking about the Titans, stars born with 20, 30, 40 times the mass of our sun, or more. Stars so massive and so luminous that they burn through their nuclear fuel at a reckless, profligate pace, living fast and dying young, sometimes in just a few million years. These are the stars that shape galaxies. Their powerful stellar winds sculpt the interstellar medium. Their intense, ultraviolet radiation ionizes vast clouds of gas, and when they die, they do so with a violence that reverberates across the cosmos. A star like this spends most of its life fusing hydrogen into helium in its core, just like any other star. But because it's so massive, it runs through that hydrogen in a fraction of the time our sun takes. When the hydrogen is exhausted, the core contracts and heats up, and helium fusion ignites. Then helium gives way to carbon, carbon to neon, neon to oxygen, oxygen to silicon. Each new fuel burns faster than the last. Silicon fusion, the final stage, lasts only about a single day. And then it's over. The silicon has been fused into iron, and iron is the end of the line. You can't get energy by fusing iron. It's the most tightly bound nucleus in nature, the ash at the bottom of the nuclear furnace. The star has been building layer upon layer of elements, like an onion, with hydrogen on the outside and iron at the center. And now that iron core is growing, accumulating mass, getting denser and hotter, and it has no source of energy to hold itself up against gravity. What happens next takes less than a second. The iron core reaches roughly 1.4 solar masses, a threshold known as the Chandrasekhar limit, and suddenly, catastrophically, it collapses. The collapse happens at a significant fraction of the speed of light. Electrons are crushed into protons, forming neutrons and releasing a flood of neutrinos so intense that despite being particles that barely interact with anything, they carry away more energy than the rest of the observable universe is producing at that moment. The core compresses until the neutrons are packed so tightly that the strong nuclear force kicks in, creating a bounce that sends a shock wave racing outward through the star. In a normal massive star, this is a supernova. The shock wave, energized by neutrinos, blows apart the outer layers of the star, creating a brilliant explosion visible across millions of light years. A neutron star is left behind, perhaps 24 miles across, spinning rapidly and enormously dense. But for the most massive stars, especially those that have been stripped of their outer hydrogen and helium envelopes, stars known as Wolf-Rayet stars, the story can go very differently. If the star is massive enough, and if it's rotating rapidly enough, the collapse doesn't stop at a neutron star. It keeps going. The core caves in on itself entirely, forming a black hole. And this is where the gamma ray burst is born. The formation of the black hole doesn't happen cleanly. As the core collapses, surrounding material, the remnants of the star's silicon and oxygen layers, begins to swirl inward, forming a superheated accretion disk around the newborn black hole. This disk is incredibly hot, incredibly dense, and incredibly magnetized. And within seconds, it does something extraordinary. It launches two narrow jets of material from the poles of the black hole, accelerated to 99.99% of the speed of light. These jets, powered by the gravitational energy of matter falling into the black hole, and shaped by powerful magnetic fields, are beams of concentrated destruction. They are narrow, typically only a few degrees wide, like cosmic spotlights aimed in opposite directions, and they have to fight their way out. Remember, this is happening inside a dying star. The jets must punch through the remaining outer layers of stellar material before they can escape into space. This takes several seconds, during which the jets drill through the star like a blowtorch through tissue paper. The interaction between the jets and the stellar material heats and compresses the surrounding gas, creating a hot cocoon that helps collimate the jets even further. When the jets finally break through the surface of the star, the gamma ray burst ignites. The exact mechanism that produces the gamma rays is still debated, but the leading model involves internal shocks. The central engine, the black hole and its accretion disk, doesn't produce a smooth, steady jet. Instead, it ejects material in spurts, like a shaky garden hose. Faster-moving blobs of material catch up to slower-moving ones within the jet, and when they collide, they create shock waves that accelerate particles to tremendous energies. These particles then radiate gamma rays through a process called synchrotron radiation, spiraling around magnetic field lines and releasing photons at the highest energies on the electromagnetic spectrum. This is the prompt emission, the initial flash of gamma rays that our satellites detect from across the universe. It can last from a few seconds to several minutes, reflecting the activity of the central engine deep inside the collapsing star. The complex, spiky light curves that we observe, with their multiple peaks and valleys, are a direct record of the chaotic, episodic nature of the jet production. Meanwhile, the jets continue to plow outward at nearly the speed of light, slamming into the gas and dust that surrounds the dying star. This interaction creates the afterglow, a longer-lasting emission that can be observed in X-rays, optical light, and radio waves for days or weeks after the initial burst. The afterglow fades gradually, following a predictable power law decline as the shock wave decelerates and cools. This scenario, the collapse of a rapidly rotating massive star into a black hole with the production of relativistic jets, is called the collapsor model. It was introduced by American astronomer Stan Woosley of the University of California, Santa Cruz, in 1993. And it has become the standard framework for understanding long-duration gamma-ray bursts. The definitive observational proof came in 2003 with GRB 30,329. This burst, detected by NASA's HET-2 satellite, was relatively nearby, just 2.65 billion light-years from Earth. Its optical afterglow was unusually bright, allowing detailed spectroscopic monitoring with the Very Large Telescope in Chile. And as the afterglow faded over the following weeks, a new spectral signature emerged beneath it, the unmistakable fingerprint of a supernova. Not just any supernova, but a particularly energetic one, a hypernova with material ejected at more than 10% the speed of light. It was the smoking gun, a gamma-ray burst and a hypernova occurring simultaneously at the same location in the same galaxy. The collapsor model was confirmed. Long gamma-ray bursts were the death cries of the most massive stars in the universe, collapsing into black holes and unleashing jets of relativistic fury. But before we get to the other kind of burst, the short ones lasting less than 2 seconds, let's take a moment to consider something that raw data and equations can't quite capture. Let's do something a little different. Let's use our imagination and ask, what would it actually look like, up close, if you could somehow witness a gamma-ray burst in person? Not from 7.5 billion light-years away, the way we observed GRB 80,319 billion, but from, say, a few light-years out, close enough to appreciate the scale of what's happening, but hopefully far enough to survive. Well, maybe. Let's say you're in a spacecraft, parked a safe distance from a massive Wolf-Rayet star in a distant galaxy. You know this star is nearing the end of its life. It's been burning through its nuclear fuel with a kind of desperate intensity. The outer layers long since blown away by its ferocious stellar wind. What remains is a brilliant, impossibly hot ball of helium, carbon, and oxygen. Maybe 10 to 15 solar masses crammed into a volume not much larger than the sun. Its surface temperature exceeds 100,000 degrees, several times hotter than the surface of our own star. It glows with a fierce blue-white light, and its stellar wind pushes outward at thousands of miles per second, carving a bubble of hot, thin gas in the surrounding interstellar medium. You've been watching this star for days, your instruments monitoring its output. And then, without warning, the star's luminosity begins to change. Not dramatically at first, a slight dimming perhaps, as the core undergoes its final convulsions. deep inside, hidden from your view, silicon is being fused into iron at a frantic pace, the last gasp of a dying nuclear furnace. You don't see it happening, but your neutrino detectors go absolutely wild. A flood of neutrinos, ghostly particles that hardly interact with matter at all, is pouring out of the star's core. In the span of about 1 second, the core releases more energy in neutrinos than the entire rest of the observable universe is putting out in all forms of radiation combined. And then the star, sort of, implodes. The light from the surface takes a moment to respond, but within seconds, you see it. The star begins to brighten, not uniformly, but in a lopsided, asymmetric way. Something is happening inside, something violent and directional. And then, if you happen to be positioned along one of the poles of the star's rotation axis, you see something that defies description. A beam of light, blindingly intense, erupts from the star's surface. It's not like a searchlight or a laser. It's more like a wound in space-time, a concentrated pillar of energy so bright that your ship's instruments saturate instantly. The light isn't just visible light. It's everything: gamma rays, X-rays, ultraviolet, optical, infrared, all blended into one devastating torrent. The jet, punching through the remaining shell of the star at 99.99% of the speed of light, is so narrow and so focused that it looks almost like a geometric impossibility. A line of fire stretching from the dying star out into infinity. The star itself is tearing apart. The regions around the jet are heated to billions of degrees, and the stellar material is being shredded, scattered, and flung outward in a catastrophic explosion. The supernova, or rather the hypernova, begins to bloom around the jet. A spherical shockwave of expanding debris laced with freshly synthesized radioactive elements. Nickel-56, cobalt-56, iron, the ashes of the universe's most extreme forge. If you're positioned off-axis, away from the jet, you'd see the hypernova itself. A spectacular, brilliant explosion that would be the most luminous thing in its host galaxy for weeks, but you'd miss the gamma ray burst entirely. The jet's radiation is focused so narrowly that it's only visible to observers within a few degrees of the jet axis. If you are in the path of the jet, well, your spacecraft doesn't last very long. The radiation field would strip away your ship's hull in microseconds, ionizing every atom in its path. But in those final moments, you would have witnessed the most energetic event in the universe, a spectacle that makes supernovae look like firecrackers. Of course, this is all speculation. No human will ever witness a gamma ray burst up close, and that's probably for the best. But the exercise of imagining it helps us appreciate the sheer scale and violence of these events. They are not just data points in a catalog. They are real, physical processes happening to real, physical objects, and they involve energies so far beyond our everyday experience that they border on the incomprehensible. Before we go any further, it's worth pausing for a moment to talk about what gamma rays actually are. Because, unless you have a background in physics, the term might feel a little abstract. We hear gamma rays, and we know they're dangerous. We know they're associated with nuclear stuff. But what are they really? All light is electromagnetic radiation, the light you see with your eyes, the radio waves that carry your favorite songs, the X-rays that reveal your bones at the doctor's office, the microwaves that heat your leftovers. These are all the same fundamental phenomena. They're all waves of oscillating electric and magnetic fields, traveling through space at 186,000 miles per second. The only thing that distinguishes one type from another is the wavelength, or equivalently, the energy. Radio waves have long wavelengths, sometimes meters or even kilometers long, and very low energy per photon. Visible light has wavelengths measured in hundreds of nanometers, about 1,000 times smaller than the width of a human hair. X-rays are smaller still, on the scale of atoms. And gamma rays are the shortest wavelength, highest energy photons in the entire electromagnetic spectrum. A single gamma ray photon can carry millions or even billions of times more energy than a photon of visible light. When we say gamma ray burst, we're saying that a colossal amount of this extremely high energy radiation arrives from a specific direction in space over a very short period of time. The photons carry so much energy individually that they can shatter atomic nuclei, tear electrons from atoms, and, in the extreme conditions near their source, even collide with each other and spontaneously create pairs of matter and antimatter particles. Here on Earth, gamma rays are absorbed by the atmosphere. You can't see them. You can't feel them unless the dose is high enough to damage your cells, in which case you have much bigger problems. That's why we need satellites to detect cosmic gamma ray bursts. The gamma rays never reach the ground. They're absorbed high in the atmosphere, which is actually a very good thing for all living things on the planet. But just because we can't see them directly doesn't mean they don't affect us. As we discussed, a nearby gamma ray burst could wreak havoc on our atmosphere's ozone layer, and the highest energy gamma rays from the most powerful bursts produce cascades of secondary particles when they hit our atmosphere. Cascades that can be detected from the ground using specialized telescopes that observe the faint flashes of Cherenkov radiation produced as these particles travel through the air faster than light travels through the same medium. So gamma ray burst astronomy exists in this fascinating dual realm. The bursts themselves are detected by instruments in orbit, above the protective blanket of our atmosphere, but some of the most energetic emissions can be studied from the ground, using the atmosphere itself as a detector. It's a beautiful example of how physicists have learned to turn an apparent limitation. We can't see gamma rays from the surface into an advantage to truly appreciate how astronomers pieced together the gamma ray burst puzzle. You need to understand something about light itself and about how desperately hard it is to study gamma rays compared to, say, the warm optical glow of a nearby star. When astronomers study a distant galaxy or a nebula in visible light, they have centuries of refined tools at their disposal. They can spread that light out into a rainbow, a spectrum, and read it like a fingerprint. Every element in the periodic table absorbs and emits light at specific wavelengths. Hydrogen has its signature. Iron has its own. Calcium, sodium, silicon. Each leaves a distinctive mark. By reading these spectral lines, astronomers can determine the chemical composition of an object, its temperature, its velocity through space, even whether it's spinning. It's an astonishingly rich source of information, and visible light spectroscopy has been the backbone of astrophysics for well over a century. But gamma rays are a different beast entirely. You cannot focus gamma rays with a lens. They pass straight through glass, through mirrors, through pretty much everything. You can't build a gamma ray telescope the way you build an optical telescope, with a big curved mirror that gathers and focuses the light to a point. Instead, gamma ray detectors rely on completely different principles. Some use scintillation crystals, materials that produce a tiny flash of visible light when a gamma ray photon strikes them. Others use semiconductor detectors that generate an electrical pulse when a gamma ray ionizes atoms within the detector material. Still, others use a technique called Compton scattering, where the gamma ray bounces off an electron inside the detector, and the angle and energy of the scattered photon are used to reconstruct the original direction and energy of the incoming ray. Each of these methods has limitations. The angular resolution of gamma ray instruments, their ability to pinpoint exactly where in the sky a signal is coming from, is dramatically worse than optical telescopes. The Fermi Gamma Ray Space Telescope, one of the best gamma ray observatories ever built, has an angular resolution of about 0.1 degrees at best for its highest energy detections. Compare that to the Hubble Space Telescope, which can resolve details as small as 0.05 arcseconds, roughly 7,000 times sharper. Trying to find the source of a gamma ray burst with a gamma ray detector alone is like trying to identify which house on a street is on fire while wearing extremely blurry glasses. You know roughly where to look, but the precise location is maddeningly uncertain. This is exactly why the afterglow revolution was so transformative. Once astronomers could detect the X-ray and optical afterglow of a burst, they could use their vastly more precise optical and radio telescopes to pinpoint the location, identify the host galaxy, and measure the distance. The gamma ray detection told them something extraordinary had happened. The afterglow told them where, how far, and in what kind of environment. And then there's the question of what the gamma ray spectrum itself tells us. Unlike visible light spectra, which are rich with narrow absorption and emission lines, gamma ray burst spectra tend to be smooth, broad, featureless curves. They're typically described by a mathematical function called the band function, named after David Band, who proposed it in 1993. This function has a characteristic shape, a low-energy power law that smoothly transitions to a steeper high-energy power law, with a peak energy somewhere in between. That peak energy, often denoted E-peak, varies from burst to burst, but typically falls in the range of 100 to 300 kiloelectronvolts for long bursts, and somewhat higher for short bursts. The smoothness of the spectrum is itself informative. It tells us that the gamma rays are not being produced by the thermal radiation of hot gas, which would produce a different spectral shape. Instead, the emission is almost certainly non-thermal, meaning it's generated by particles that have been accelerated to extreme energies by some mechanism other than simple heating. The leading candidate is synchrotron radiation, the light emitted by electrons spiraling in intense magnetic fields at nearly the speed of light. This is consistent with the fireball model's picture of internal shocks within the jet, where colliding shells of material create magnetic turbulence and accelerate electrons to the energies needed to produce gamma rays. but the details remain stubbornly uncertain. The exact mechanism that converts the jet's kinetic energy into the observed gamma ray emission is still one of the biggest open questions in the field. Is it synchrotron radiation from shock-accelerated electrons? Is it inverse Compton scattering, where high-energy electrons boost low-energy photons to gamma-ray energies? Is it photospheric emission from the jet's surface, or some combination of all three? Different models predict subtly different spectral shapes, and the observations have not yet been able to definitively distinguish between them. This is, in fact, one of the deepest unsolved problems in gamma-ray burst physics. We understand the broad strokes of how the explosion works. We know the progenitors. We can model the jets and predict the afterglows, but the precise mechanism by which those jets convert their enormous kinetic energy into the prompt gamma-ray flash that we actually detect, that remains, frustratingly elusive. And so spectroscopy, in its various forms, continues to be one of the primary tools for cracking this remaining mystery. Every new burst detected by Fermi or by future missions adds another data point, another spectrum to analyze, another piece of the puzzle. Somewhere in those smooth, featureless curves lies the answer. We just haven't found it yet. Let's go back to those confused decades between the first detection in 1967 and the breakthrough of afterglow discovery in 1997, because those 30 years weren't just a period of waiting. They were a period of frantic, often frustrating, and occasionally brilliant scientific work that laid the groundwork for everything that came after. After Klebesadel's 1973 paper announced gamma-ray bursts to the world, the astronomical community responded with an enthusiasm that bordered on frenzy. Theorists proposed model after model. Experimentalists scrambled to build better detectors. And a cottage industry of gamma-ray burst conferences sprang up, where heated debates over the nature and origin of these mysterious flashes became legendary. One of the earliest and most creative efforts to localize gamma-ray bursts came from the Interplanetary Network, or IPN. The concept was straightforward. If you have gamma-ray detectors on spacecraft scattered throughout the solar system, you can use the differences in arrival times of a burst at each detector to triangulate the position of the source. The farther apart the detectors, the better the triangulation. By the late 1970s, the IPN included detectors on the Vela satellites in Earth orbit, on the Russian Prognoz 7 satellite, on the German Helios 2 probe in solar orbit, and on NASA's Pioneer Venus orbiter circling Venus. Later editions included instruments on Ulysses, which was studying the Sun from a polar orbit, and on various Mars missions. This network could sometimes localize bursts to error boxes just a few arc minutes across, a dramatic improvement over the degree scale positions from individual satellites. And yet, even with these improved positions, no counterpart was ever found. Astronomers pointed optical telescopes at the error boxes, searching for anything that looked unusual. A fading star, a peculiar galaxy, any kind of transient source. Nothing. The gamma-ray bursts left no trace at any other wavelength. They appeared, they flashed, and they vanished without a footprint. This absence of counterparts was deeply puzzling and contributed to the proliferation of theoretical models. Some proposals were quite clever. One idea, championed by some Soviet physicists, suggested that gamma-ray bursts came from the surface of neutron stars, powered by sudden rearrangements of the star's magnetic field, a process now known to produce related but distinct phenomena called soft gamma repeaters and magnetar flares. Another proposal involved the collision of asteroids or comets with neutron stars, the kinetic energy of the impact being converted into a burst of gamma radiation. A particularly elegant model, proposed by Boden-Paksinski in 1986, suggested that gamma-ray bursts might come from the merger of binary neutron stars at cosmological distances. This was prescient. It turned out to be correct for short gamma-ray bursts, though Paksinski proposed it as a general model for all bursts. The paper was largely ignored at the time because most of the community still believed gamma-ray bursts were galactic phenomena, and the energy requirements for a cosmological model seemed absurd. Throughout the 1980s, the most popular models involved neutron stars within the Milky Way, primarily because this kept the energy requirements manageable. A burst from a neutron star a few hundred light years away didn't need to be all that energetic to explain the observed signals. But the BATSE data from the early 1990s, showing that isotropic distribution across the sky, gradually eroded support for galactic models. And then BEPO-SAX provided the killing blow with those first afterglow detections. It's worth noting that the 30-year mystery of gamma-ray bursts stands as one of the longest unsolved puzzles in modern astrophysics. Pulsars were explained within months of their discovery. Quasars took a few years. Even the cosmic microwave background radiation was understood fairly quickly after its detection, but gamma-ray bursts resisted explanation for 3 decades. It was humbling, and it served as a reminder that the universe doesn't always yield its secrets on our preferred timeline. We touched on the collapsar model earlier, but the progenitor stars, the Wolf-Rayet stars, deserve a closer look. These are some of the most extreme objects in the stellar zoo, and understanding them is key to understanding why only some massive stars produce gamma-ray bursts. Wolf-Rayet stars are named after the French astronomers Charles Wolf and Georges Rayet, who first identified their unusual spectra in 1867. Unlike normal stars, which show dark absorption lines in their spectra, where specific wavelengths of light are absorbed by the star's atmosphere, Wolf-Rayet stars show bright emission lines. These emission lines indicate that the star is surrounded by a dense, fast-moving stellar wind. Material being blasted off the star's surface at speeds of 1,000 to 3,000 miles per second. What makes Wolf-Rayet stars so important for gamma-ray burst science is their composition. These are massive stars that have lost their outer envelopes of hydrogen, and sometimes helium too, exposing the hot, dense layers beneath. They are, in a sense, naked stellar cores, the beating hearts of what were once much larger stars, now stripped down to their essentials. There are several ways a star can become a Wolf-Rayet. The most straightforward is simply through powerful stellar winds. A very massive star, say 40 or 50 times the mass of the Sun, has such an intense radiation field that it literally blows its own outer layers into space over the course of its relatively short life. by the time it reaches the end of its hydrogen-burning phase, it may have lost a significant fraction of its original mass. Another route involves binary interactions. If a massive star has a companion, mass transfer between the two stars can strip the primary of its hydrogen envelope more efficiently than winds alone. This binary stripping mechanism is increasingly recognized as an important pathway to producing the rapidly rotating stellar cores that the collapsar model requires. And here's the critical point about rotation. Not every massive star that collapses will produce a gamma-ray burst. To launch relativistic jets, the collapsing core needs to have a substantial amount of angular momentum. It needs to be spinning fast. This is because the formation of the accretion disk around the newborn black hole, which is essential for powering the jets, requires material with enough angular momentum to avoid falling directly into the black hole. Without a disk, there's no jet. Without a jet, there's no gamma-ray burst. You get a supernova, perhaps a very energetic one, but not a GRB. The challenge is that the same stellar winds that strip a massive star of its hydrogen also tend to carry away angular momentum, slowing the star's rotation. It's a catch-22. You need to lose the hydrogen envelope to become a Wolf-Rayet star, so the jet can escape. But the process of losing that envelope also spins you down, which prevents the jet from forming in the first place. There are potential solutions. One is that the Wolf-Rayet phase is very short, so there isn't time for much spin down to occur. Another is that the star has low metallicity, few elements heavier than hydrogen and helium, which means weaker stellar winds and less angular momentum loss. This may explain why long gamma-ray bursts are preferentially found in galaxies with low metallicity. The conditions are more favorable for producing the rapidly rotating Wolf-Rayet stars that become gamma-ray burst progenitors. A third possibility involves binary systems where a companion star tidally spins up the Wolf-Rayet star just before it collapses. This would allow the core to retain enough angular momentum to form a disk and launch jets, even if the stellar winds have been relatively strong. The bottom line is that gamma-ray bursts are rare events, even among the deaths of massive stars. Only about 1 out of every 1,000 core collapse supernovae produces a gamma-ray burst. The conditions have to be just right. The right mass, the right metallicity, the right rotation rate, the right moment in stellar evolution. It's a cosmic lottery, and the odds are long. But the universe has a lot of tickets. The detection of G100 and 70,817 and its associated short gamma-ray burst didn't just confirm that neutron star mergers produce short bursts. It inaugurated an entirely new era of astronomy, multi-messenger astrophysics. For thousands of years, we've studied the universe using light. Visible light first, then radio waves, infrared, ultraviolet, X-rays, and gamma rays as new instruments were developed. All of these are forms of electromagnetic radiation, all traveling at the speed of light, all providing different but related views of the same cosmic phenomena. Gravitational waves are something fundamentally different. They're not electromagnetic radiation. They're ripples in the fabric of space-time itself, produced by the acceleration of massive objects. They travel at the speed of light, but they interact with matter so weakly that they pass through everything, stars, planets, galaxies, almost without effect. This makes them incredibly difficult to detect, but it also means they carry information about events that electromagnetic radiation cannot reveal, like the moments just before and during the merger of two black holes, when no light is emitted at all. The Laser Interferometer Gravitational Wave Observatory, LIGO, achieved the first direct detection of gravitational waves on September 14, 2015, from the merger of two black holes about 1.3 billion light-years away. That historic detection earned the Nobel Prize in Physics for Kip Thorne, Rainer Weiss, and Bari Barish, and it opened a window onto the universe that had been closed since the beginning of time. But black hole mergers don't produce electromagnetic radiation, at least not typically. So the 2017 detection of G170,817, a neutron star merger, was the first time gravitational waves and electromagnetic radiation were observed from the same event, and the scientific yield was extraordinary. The gravitational wave signal told us the masses of the two neutron stars, between 1.1 and 1.6 solar masses each, the orbital dynamics of the merger, and the approximate distance. The gamma-ray burst confirmed the connection between neutron star mergers and short bursts. The kilonova emission confirmed the production of heavy elements through the R process. The X-ray and radio afterglows, which appeared days and weeks later, revealed the structure and evolution of the relativistic jet and its interaction with the surrounding medium. And the time delay between the gravitational waves and the gamma rays, just 1.7 seconds, provided a stunning test of Einstein's general relativity. It confirmed that gravitational waves and light travel at the same speed to within 1 part in a quadrillion. This single measurement ruled out or constrained a number of alternative theories of gravity that had been proposed as modifications to general relativity. The event also provided a new and independent measurement of the Hubble constant, the rate at which the universe is expanding. By combining the distance inferred from the gravitational wave signal with the redshift of the host galaxy, astronomers obtained a value of about 70 kilometers per second per megaparsec, broadly consistent with existing measurements, but with enough uncertainty that more events will be needed to make a precise determination. The promise of multi-messenger astronomy is that by combining information from different types of signals, gravitational waves, electromagnetic radiation, and eventually neutrinos, we can build a much more complete picture of cosmic events than any single messenger could provide. Gamma-ray bursts, which produce signals across all of these channels, are at the very heart of this revolution. As gravitational wave detectors become more sensitive, LIGO and Virgo have undergone several upgrades, and new detectors like KAGRA in Japan and the planned Einstein telescope in Europe will join the network. We expect to detect more neutron star mergers, more short gamma-ray bursts, and more opportunities to study these events in unprecedented detail. Each one will teach us something new about the physics of extreme matter, the origin of heavy elements, and the fundamental nature of gravity. Despite all that we've learned, gamma-ray bursts still hold many secrets. Let me walk through some of the biggest open questions in the field. First, there's the prompt emission puzzle. We know that the gamma rays are produced in the relativistic jet, most likely through internal shocks or magnetic reconnection events, but the detailed spectral shape of the prompt emission doesn't perfectly match any simple theoretical model. The observed spectra are often described by what's called a band function, named after David Band, who first proposed it, a smooth, broken power law shape with a peak energy typically in the range of a few hundred kiloelectron volts. While synchrotron radiation from shock-accelerated electrons can produce something like this, the fit isn't perfect. Some bursts show spectral features that are hard to explain with synchrotron emission alone. And there are ongoing debates about whether thermal, photospheric, emission from the jet itself might play a significant role. The boat added a tantalizing new clue to this debate. Analysis of Fermi data from GRB 221009 A revealed an emission line at about 12 million electron volts, appearing about 5 minutes after the burst was detected. This is potentially the first high-confidence spectral emission line ever detected in a gamma ray burst, after 5 decades of searching. The team believes it may come from the annihilation of electrons and positrons in the jet, which would provide unprecedented insight into the composition and physics of the outflow. But more events with similar features will be needed to confirm this interpretation. Second, there's the question of ultra-long gamma ray bursts. Most long bursts last from a few seconds to a few minutes, but a handful of events, like GRB 101225A and GRB 111209A, lasted for thousands of seconds, far longer than the collapse model naturally predicts. These ultra-long bursts may require a different progenitor altogether. Perhaps the collapse of a blue supergiant star with a much larger envelope that takes longer for the jet to traverse. Or perhaps a tidal disruption event where a star is torn apart by a black hole. The exact nature of ultra-long gamma ray bursts remains an active area of research. Third, there's growing evidence that the neat division between long equals collapsor and short equals merger is breaking down. The discovery of kilonovae associated with some long-duration bursts, like GRB 211211A and GRB 230307A, suggests that neutron star mergers can, in some circumstances, produce extended gamma ray emission lasting tens of seconds. This blurs the traditional classification scheme and suggests that the physical processes at work may be more diverse than previously thought. And fourth, there's the fundamental question of whether gamma ray bursts can teach us new physics. The extreme energies, densities, and velocities involved in these events create conditions that simply cannot be reproduced in any laboratory. By studying the behavior of matter and radiation under these conditions, we may be able to test theories of quantum gravity, probe the equation of state of nuclear matter at supernuclear densities, constrain models of dark energy, and explore the boundaries of known physics in ways that no other phenomenon allows. Gamma ray bursts are, in a very real sense, the universe's own particle accelerators, operating at energies that dwarf anything we can build on Earth. And every new burst we detect is another experiment, another data point, another chance to learn something unexpected about the fundamental laws that govern reality. One of the most remarkable aspects of modern gamma-ray burst science is the global network of telescopes and scientists that has been built up over the decades to study these fleeting events. Because bursts are unpredictable, appearing anywhere in the sky at any time, studying them requires a level of coordination and rapid response that is unique in astronomy. The system works like this. When a satellite like Fermi or Swift detects a gamma-ray burst, it automatically calculates the burst's approximate position and transmits it to the ground within seconds via the Gamma-Ray Coordinates Network, or GCN. This network distributes the alert to hundreds of observatories around the world, from major research facilities to small robotic telescopes, many of which have been programmed to respond automatically. Some of these robotic telescopes can slew to the burst position and begin imaging within seconds of receiving the alert. This rapid response is critical because the early afterglow contains the most information: the brightness, the color, the rate of fading, any spectral features. All of these are best measured while the afterglow is still bright. Once it fades, much of the information is lost forever. The result is a remarkable collaboration that spans continents, time zones, and institutional boundaries. When a bright burst goes off, emails and messages fly around the world within minutes. Telescope operators on mountaintops in Chile, Hawaii, the Canary Islands, and Arizona all receive the same alert and spring into action. Within hours, a picture of the event begins to emerge, assembled from data gathered by dozens of instruments, each contributing its own piece of the puzzle. It's science at its best: fast, collaborative, and driven by the pure excitement of discovery. Every gamma-ray burst is unique, and you never know which one will be the next record breaker, the next paradigm shifter, the next event that forces us to rethink what we thought we knew. If long gamma-ray bursts are the death screams of massive stars, then short gamma-ray bursts are something altogether different. They are the final act of a cosmic dance that can take billions of years to complete, a slow, elegant spiral that ends in one of the most violent collisions imaginable. Imagine two neutron stars, each one the compressed corpse of a once great star. Each is roughly 12 miles across, but contains 1.5 times the mass of our sun. A sugar cube-sized chunk of neutron star material would weigh about 1 billion tons on Earth. These are objects of almost incomprehensible density, surrounded by magnetic fields trillions of times stronger than Earth's, spinning hundreds of times per second. Now imagine that these two objects are orbiting each other, locked in a gravitational embrace. This can happen when two massive stars in a binary system both end their lives as supernovae, each leaving behind a neutron star remnant. If the system survives both explosions, and many don't, the two neutron stars are left circling each other in the debris. And here's where Einstein enters the picture. According to general relativity, two massive objects orbiting each other will generate gravitational waves, ripples in the fabric of space-time itself. These ripples carry away energy from the system, and as energy is lost, the orbit shrinks. The neutron stars inch closer together, their orbital speed increasing as they spiral inward. It's a process that takes an agonizingly long time. For a typical neutron star binary, the inspiral can last tens of millions, even billions of years. But gravity is patient. Slowly, imperceptibly, the two neutron stars creep toward each other. The orbital period decreases from hours to minutes to seconds. In the final moments, they're whipping around each other hundreds of times per second. The gravitational waves they produce growing stronger and higher in frequency, like a cosmic chirp rising in pitch toward a climax, and then they touch. When two neutron stars collide at roughly a third of the speed of light, the result is, well, it's hard to overstate the violence. Tidal forces rip the stars apart in the final milliseconds before contact. Neutron-rich material is flung outward in all directions. The collision creates temperatures of hundreds of billions of degrees, far hotter than the core of any star. A massive shockwave propagates through the merged remnant. Magnetic fields are amplified to mind-boggling strengths within milliseconds. And, depending on the combined mass, the remnant either briefly forms an ultramassive neutron star that quickly collapses into a black hole, or it forms a black hole almost immediately. Around this newborn black hole, an accretion disk forms, just as in the collapsor model. And just like in the collapsor model, relativistic jets are launched from the poles, blasting outward at nearly the speed of light. These jets produce the gamma ray burst itself. But because the whole process, from collision to black hole formation to jet launch, happens so quickly, the resulting burst is short. Less than 2 seconds, often just a few hundred milliseconds. That's your short gamma ray burst. The product of a collision billions of years in the making, consummated in the blink of an eye. For decades, this was the leading theoretical model for short gamma ray bursts. It was elegant and compelling. But it remained unproven until one extraordinary day in August 2017, a day that would go down as one of the most important in the history of astronomy. On August 17th, 2017, at 12:41 Universal Time, the LIGO Gravitational Wave Observatory in the United States and the Virgo detector in Italy registered a signal. It was the distinctive chirp of two objects spiraling into each other, growing louder and higher pitched over about 100 seconds before cutting off abruptly. The signal was consistent with two neutron stars merging. This event was designated G100 and 70,817. Just 1.7 seconds after the gravitational wave signal ended, NASA's Fermi Gamma Ray Space Telescope detected a short gamma ray burst, designated GRB 170,817A, coming from the same region of the sky. Let that sink in. Gravitational waves and gamma rays arriving within less than 2 seconds of each other, from the same direction, from the same event. The connection between neutron star mergers and short gamma ray bursts, theorized for decades, was confirmed in a single, breathtaking observation. But the story doesn't end there. In fact, it was just beginning. Within hours, an alert went out to telescopes around the world. The rough position provided by the gravitational wave detectors and the gamma ray instruments was refined, and observatories began scanning the indicated region of the sky. 11 hours after the merger, a team using the SWOPE telescope in Chile spotted it. A new point of light in the outskirts of an elliptical galaxy called NGC 4993, about 100 and 30 million light-years from Earth. It was designated SSS 17A, later known more formally as Kilonova AT 2017 GFO. Over the following days and weeks, more than 70 observatories around the world trained their instruments on this single point of light. It was observed across the entire electromagnetic spectrum, from radio waves to X-rays to gamma rays. It was the most intensely studied astronomical event in history, generating dozens of scientific papers published simultaneously, a scientific event so massive that it fundamentally changed our understanding of the universe. And one of the most profound revelations was about where the gold in your jewelry comes from. See, when those two neutron stars collided and flung out their neutron-rich debris, the conditions were perfect for something called the R process, or rapid neutron capture process. In this nuclear reaction, atomic nuclei are bombarded with neutrons so fast that the nuclei don't have time to decay between captures. The result is the creation of extremely heavy elements, elements heavier than iron, elements that cannot be forged in the cores of ordinary stars. Elements like platinum, gold, uranium, and many others. The spectral analysis of the kilonova from G170,817 confirmed it. The fading glow showed unmistakable signatures of heavy elements, including lanthanides, created in the merger. Estimates suggest that this single event produced roughly 16,000 times the mass of the Earth in heavy elements, including about 10 Earth masses of gold and platinum. Think about that the next time you look at a gold ring. Those atoms were forged in the collision of neutron stars billions of years ago, scattered into the interstellar medium, incorporated into the cloud of gas and dust that eventually collapsed to form our sun and planets. The gold on your finger is the product of a gamma ray burst. We've talked about what causes gamma ray bursts: collapsing massive stars for the long ones, merging neutron stars for the short ones, but we've only scratched the surface of how the actual burst is produced. The physics of the jets themselves is some of the most extreme and fascinating in all of astrophysics, and it's worth spending some time in the engine room. The central concept is the fireball model, developed in the 1990s by theorists like TSVI Perrin and Peter Messeros. In this framework, the central engine, whether a newborn black hole from a collapsor or from a neutron star merger, produces an outflow of energy so intense that it creates a fireball, a dense, opaque cloud of radiation, electron-positron pairs, and a small admixture of ordinary matter, protons and neutrons. This fireball is extraordinarily hot and under enormous pressure, and it expands outward at nearly the speed of light. Now, here's where it gets interesting. As the fireball expands, it cools, and most of its thermal energy is converted into the kinetic energy of bulk motion. The material is now moving at Lorentz factors of hundreds, meaning it's traveling at 99.99% of the speed of light. At these velocities, relativistic effects become dominant, and the physics gets wonderfully strange. The key to producing the observed gamma rays is believed to be internal shocks. The central engine doesn't produce a uniform jet. Instead, it ejects material in irregular pulses, some faster than others. When a faster pulse catches up to a slower one within the jet, The collision creates a shock wave that heats the material and accelerates electrons to very high energies. These energetic electrons spiral around magnetic field lines and emit synchrotron radiation, which is what we observe as the prompt gamma ray emission. But there's a puzzle here. If you calculate the energy being emitted and the size of the emitting region, which you can infer from the short timescale variability of the light curves, you run into what's called the compactness problem. The radiation should be so intense and so concentrated that photons would collide with each other and create electron-positron pairs, making the source completely opaque to its own radiation. In other words, you shouldn't be able to see the gamma rays at all. They should be trapped. The solution is the relativistic motion itself. Because the material is moving toward us at nearly the speed of light, all the timescales are compressed, and the apparent size of the emitting region is much larger than the true size. This dilutes the radiation enough to allow the gamma rays to escape. The compactness problem was actually one of the earliest and strongest arguments that gamma ray bursts must involve ultra-relativistic motion, long before we had direct evidence for it. Another critical aspect is beaming. Gamma ray burst jets are not spherical explosions. They are narrow, focused beams, typically with opening angles of only a few degrees. This has profound implications. First, it means that we can only see a gamma ray burst if the jet happens to be pointed roughly in our direction. For every burst we detect, there are hundreds, perhaps even 500, that we miss because their jets are aimed elsewhere. This means gamma ray bursts are actually far more common than the detection rate suggests. Second, beaming dramatically reduces the total energy budget. If you assume the energy is emitted isotropically, equally in all directions, you calculate absurdly high energies, 10 to the 53rd or 54th power ergs. But if the energy is concentrated into a narrow jet occupying only a small fraction of the full sphere, the true energy is much lower, perhaps 10 to the 51st power ergs. That's still an extraordinary amount, roughly equivalent to the total kinetic energy of a supernova. But it's physically achievable. It doesn't require invoking new physics. The boat event, GRB 221009A, provided a remarkable case study in jet physics. Follow-up observations with NASA's New Star Observatory revealed that its jet had an unusual structure, a narrow, ultra-fast core surrounded by a wider, slower wing, with the energy varying at different distances from the core's center. This structured jet model had been theorized before, but never so clearly observed. It suggests that the internal dynamics of the collapsing star, its mass, density profile, and magnetic field, directly shape the geometry of the jet that emerges. Every gamma ray burst is a unique experiment in extreme physics, a natural laboratory producing conditions that we could never replicate on Earth. We've mentioned beaming several times, but it's worth diving deeper into this concept because it fundamentally changes how we think about gamma ray bursts and what they tell us about the universe. When a gamma ray burst occurs, the jet is typically only a few degrees wide. This means that the gamma ray emission is concentrated into a tiny fraction of the total sky as seen from the source. Imagine standing at the center of a sphere, holding a laser pointer. The laser illuminates only a tiny dot on the sphere's surface. Similarly, a gamma ray burst's jet illuminates only a small patch of the universe. This has several important consequences. First, it means that for every gamma ray burst we detect, there are many more that we don't. If the jet opening angle is, say, 5 degrees, then the solid angle covered by both jets, remember, there are two, pointing in opposite directions, is only about 1% of the total sphere. This means that for every burst we see, there are roughly 100 that are oriented such that neither jet points toward us. Some estimates put this number even higher, at 200 to 500, depending on the average jet opening angle. This dramatically increases the true rate of gamma ray bursts in the universe. We detect about 1 burst per day from all directions. If the beaming correction factor is 100, then the true rate is something like 1 burst every 15 minutes, somewhere in the observable universe. That's a lot of dying stars and merging neutron stars. Second, beaming solves the energy problem. Early estimates of gamma ray burst energies assumed the radiation was emitted isotropically, uniformly in all directions. Under that assumption, the energies were absurd, sometimes exceeding 10 to the 54th power ergs, equivalent to converting several solar masses entirely into radiation. But if the energy is concentrated into a narrow jet, the true energy is reduced by the beaming factor. A burst with an isotropic equivalent energy of 10 to the 53rd power ergs and a jet opening angle of a few degrees actually has a true energy of around 10 to the 51st power ergs. That's still enormous, roughly the kinetic energy of a supernova, but it's physically reasonable. No exotic physics is required. Third, beaming explains why some afterglows show a distinctive steepening in their light curves, the jet break we mentioned earlier. As the jet decelerates by plowing into the surrounding medium, its Lorentz factor decreases. At some point, the relativistic beaming angle becomes wider than the physical opening angle of the jet. When this happens, the observer effectively sees the edge of the jet for the first time, and the afterglow begins to fade more rapidly. The time at which this jet break occurs is directly related to the jet's opening angle, providing a crucial measurement for determining the true energy. The realization that gamma ray bursts are beamed was one of the most important advances in the field. It transformed GRBS from impossibly energetic phenomena that seemed to require new physics into, well, merely extremely energetic phenomena that could be explained within the framework of known astrophysics. Beaming turned the impossible into the improbable, and the improbable into the merely extraordinary. Gamma ray bursts have a habit of shattering records. Each new one seems to push the boundaries of what we thought was possible, and 2 events in particular stand out as the most extraordinary. The first is GRB 80,319 billion. On March 19, 2008, NASA's Swift satellite was having an unusually busy day. It had already detected 3 gamma ray bursts in the previous hours. Then, at 6:12 Universal Time, a 4th burst was detected in the constellation Boots. And this one was different, as the burst's optical afterglow brightened and was captured by ground-based robotic telescopes that were already monitoring the sky. Something astonishing happened. The afterglow reached a peak visual brightness of magnitude 5.3. That is, for a brief window of about 30 seconds. The explosion was bright enough to be seen with the naked eye. Now, under good conditions, in a dark sky, a person with normal vision can see objects down to about magnitude 6. This burst, at its peak, was brighter than that threshold. If you had been standing outside, in a dark countryside, looking at exactly the right spot in the sky at exactly the right moment, you could have seen it, a pinpoint of light, briefly flickering into existence, then fading away. And here's the mind-bending part. This burst was 7.5 billion light-years away, half the current age of the universe. Before the Earth even existed, the light from this explosion had been traveling since the universe was less than half its present age. And it was still bright enough for a human eye to detect. The afterglow was 2.5 million times more luminous than the brightest supernova ever recorded. If you had been standing just 1 astronomical unit away from this explosion, the same distance as Earth from the Sun, it would have appeared with a visual magnitude of -67. For comparison, the Sun from Earth is magnitude -26.7. This burst would have appeared over a quadrillion times brighter than the Sun at Earth's distance. Previous to this, the most distant object visible to the naked eye was the Andromeda Galaxy, a mere 2.5 million light-years away. GRB 80,319 billion shattered that record by a factor of 3,000, and then came the boat. On October 9th, 2022, GRB 221,009A arrived from a distance of about 1.9 billion light-years. It was, in astronomical terms, relatively close for a gamma-ray burst. But its proximity was only part of what made it extraordinary. The burst lasted about 10 minutes, far longer than most. Its gamma-ray emission was so intense that it overwhelmed nearly every instrument designed to measure it. The Fermi Gamma-Ray Space Telescope, one of the most sensitive gamma-ray observatories ever built, was completely saturated. Scientists had to use indirect methods to reconstruct the burst's true brightness, because the instruments literally couldn't keep up. When the numbers were finally tallied, the boat was 70 times brighter than the previous record holder. It had the highest isotropic equivalent total energy ever measured for a gamma-ray burst. Photons were detected with energies up to 18 trillion electron volts, the most energetic photons ever associated with a GRB. And one air shower event suggested a particle with energy around 300 trillion electron volts. For context, visible light photons carry just 2 to 3 electron volts of energy. The boat produced 20 distinct X-ray echo rings, triple the previous record, created by its X-rays scattering off of interstellar dust clouds within our own galaxy. It was the brightest afterglow ever recorded in X-rays, in ultraviolet, and in optical light. It was 10 times brighter than any previous GRB detected by the SWIFT mission. Eric Burns led a team that compared the boat against roughly 7,000 previously detected gamma-ray bursts. Their conclusion was sobering. An event of this magnitude is estimated to occur about once every 10,000 years. The boat may not be the brightest gamma-ray burst in all of cosmic history, but it is very likely the brightest one since the dawn of human civilization. Dan Purley, an astrophysicist at Liverpool John Moores University, said it simply: there is nothing in human experience that comes anywhere remotely close to such an outpouring of energy. Nothing. We've mentioned GRB 30,329 a couple of times, but this event is so important that it deserves its own section in the history of gamma-ray burst research. It occupies a place analogous to the Rosetta Stone in archaeology. It was the event that cracked the code and provided the definitive link between long gamma-ray bursts and the deaths of massive stars. On March 29, 2003, NASA's HET-2 satellite detected a gamma-ray burst in the constellation Leo. Within 90 minutes, a bright optical afterglow had been identified by ground-based telescopes. The burst was given the designation GRB 30,329, following the standard naming convention based on the date. What made this burst special was its relative proximity. At a distance of about 2.65 billion light-years, a redshift of 0.1685. It was among the nearest gamma-ray bursts ever detected. This proximity made it unusually bright, allowing for detailed spectroscopic observations over an extended period. Within 24 hours of the burst, the Very Large Telescope in Chile obtained a detailed spectrum of the optical afterglow. This spectrum showed a typical power law shape, characteristic of synchrotron emission from the decelerating jet. But as the days passed and the afterglow faded, something remarkable began to happen. The spectrum started to change. New spectral features began to emerge from beneath the fading afterglow. Broad bumps in the light curve, distinctive absorption lines, features that looked unmistakably like those of a supernova. Over the following weeks, the supernova component became increasingly dominant as the afterglow continued to decline. The spectrum evolved to closely resemble that of SN 1998 BW, the peculiar type Ike supernova that had been tentatively associated with GRB 900 and 80,425 5 years earlier. But this time, the connection was unambiguous. The supernova and the gamma-ray burst were happening at the same time, in the same place, producing a spectrum that bore the unmistakable fingerprint of a massive star's collapse. The supernova was designated SN 2003DH, and it was classified as a hypernova. A supernova with unusually high kinetic energy, consistent with the collapser model's prediction of an extremely energetic explosion. The velocity of the ejected material exceeded 30,000 kilometers per second, about 10% of the speed of light, testifying to the enormous power of the explosion. An international team of 27 researchers from 17 institutions published their findings, declaring that the spectral evidence provided irrefutable evidence of a direct connection between the gamma-ray burst and the hypernova explosion. Stan Woosley, who had proposed the collapser model a decade earlier, was a co-author. He noted that while the gamma-ray burst mystery wasn't fully solved, we are confident now that long bursts involve a core collapse and a hypernova, likely creating a black hole. GRB 30,329 was, in the words of many astronomers, a type-defining event. It established beyond reasonable doubt that long gamma-ray bursts are produced by the collapse of massive stars. It validated the collapser model as the correct framework for understanding these events. and it transformed gamma-ray burst science from a field wrestling with fundamental questions of origin into one focused on the detailed physics of the most extreme stellar deaths in the cosmos. If the prompt gamma-ray emission is the explosion itself, the afterglow is the slowly settling debris cloud. And it's in the afterglow that much of the real science happens. The physics of afterglows is, in some ways, more straightforward than the prompt emission. After the jet has punched through the star, in the case of a long burst, or escaped the merger debris for a short burst, it continues to barrel outward into the surrounding medium. As it does, it sweeps up interstellar gas and dust, creating a forward shock wave, much like the bow wave of a boat plowing through water. This shock wave heats the ambient material and accelerates electrons, which then emit synchrotron radiation across a broad range of wavelengths. The afterglow typically appears first in X-rays, then in optical and ultraviolet wavelengths, and finally in radio. The emission fades over time in a characteristic power law decay, meaning it decreases at a predictable rate that can be described by a mathematical formula. This decay rate contains a wealth of information. From it, astronomers can infer the energy of the blast, the density of the surrounding medium, the geometry of the jet, and the efficiency of particle acceleration in the shock. One of the most important features in afterglow light curves is the jet brake. As the jet decelerates, its relativistic beaming effect weakens. At some point, the observer begins to see the edge of the jet, and the afterglow fades more steeply. The time at which this break occurs tells you the opening angle of the jet, which in turn tells you the true total energy of the burst, as opposed to the inflated isotropic equivalent energy. NASA's Swift satellite, launched in November 2004, was specifically designed to make an afterglow science routine. When its Burst Alert telescope detects a gamma-ray burst, the entire spacecraft autonomously slews, repointing itself within 90 seconds to train its X-ray and optical telescopes on the burst location. This rapid response capability has been transformative. Before Swift, catching an afterglow was a race against time, often lost. With Swift, early afterglow observations became standard, revealing unexpected complexity, including X-ray flares, plateau phases, and erratic variability that challenged the simple models. The afterglow is also the key to connecting gamma-ray bursts with their host galaxies, and that connection opens up an entirely separate line of investigation. The afterglow is also the key to connecting gamma-ray bursts with their host galaxies. Once an afterglow has faded, deep imaging with space telescopes like Hubble or ground-based giants like the Keck Observatory can reveal the underlying galaxy, and the properties of these galaxies tell us a great deal about the environments that produce gamma-ray bursts. Long gamma-ray bursts show a strong preference for small, irregular, actively star-forming galaxies with low metallicity. This makes sense in the context of the collapsar model. Massive stars form in regions of active star formation, and the low metallicity preference is consistent with the theoretical requirement for reduced stellar wind losses, which allows the progenitor star to retain more angular momentum and produce the rapidly rotating core needed to launch a jet. Interestingly, this metallicity preference has implications for the habitability of galaxies. Our own Milky Way is a large, metal-rich galaxy. Long gamma ray bursts preferentially occur in galaxies that are chemically very different from ours. While it's not impossible for a long GRB to occur in the Milky Way, the current rate is probably quite low compared to smaller, metal-poor galaxies. This is somewhat reassuring, as it suggests that Earth is in a relatively safe galactic neighborhood, at least when it comes to this particular cosmic threat. Short gamma ray bursts, by contrast, have been found in a much wider variety of host galaxies, including large elliptical galaxies with very little ongoing star formation. This is perfectly consistent with the neutron-star merger model. Neutron-star binaries can take billions of years to spiral together and merge, so the explosion can occur long after the stars that created the neutron stars have died, and star formation in the galaxy has ceased. Some short bursts have even been found at significant offsets from their host galaxies, suggesting that the binary system received a kick from the supernova explosions that created the neutron stars and was ejected from its birthplace. The study of host galaxies has also revealed that gamma ray bursts can serve as tracers of star formation history across cosmic time. Because long bursts are associated with the deaths of short-lived massive stars, they essentially tag regions where star formation is actively occurring. By studying the rate and distribution of gamma ray bursts at different redshifts, astronomers can map out how the cosmic rate of star formation has changed over the history of the universe. This complements other methods, like studying the infrared and ultraviolet emission from distant galaxies, and provides an independent check on our understanding of how the universe evolved. So far, we've been talking about gamma ray bursts as distant cosmic fireworks, spectacular but safely remote. Every burst we've ever detected has come from outside the Milky Way. They're the universe's most powerful explosions, yes, but they've been playing out in galaxies millions or billions of light years away. But what if one happened closer to home? This is a question that some researchers have taken very seriously, and the answer is unsettling. A gamma ray burst within our own galaxy, with its jet pointed toward Earth, would be a catastrophe of almost unimaginable proportions. The primary threat wouldn't be the gamma rays themselves, at least not directly. Earth's atmosphere is thick enough to absorb gamma radiation before it reaches the surface. The real danger would come from what the gamma rays do to the atmosphere. When a pulse of intense gamma radiation strikes the upper atmosphere, it triggers a cascade of chemical reactions. Nitrogen and oxygen molecules are broken apart, and the freed atoms recombine into new compounds, most notably nitrogen dioxide and nitric oxide. These nitrogen oxides have a devastating effect on the ozone layer, Earth's protective shield against solar ultraviolet radiation. Models suggest that a gamma ray burst occurring within a few thousand light years of Earth could deplete up to half of the ozone layer within weeks. With the ozone layer compromised, ultraviolet radiation from the sun would reach the surface in vastly increased amounts. This would be devastating for photosynthetic organisms, both on land and in the upper layers of the ocean. Phytoplankton, which form the base of the marine food web, would be particularly vulnerable. On land, plants would suffer damage to their cells and reduced productivity. Animals, including humans, would face dramatically increased rates of skin cancer, cataracts, and immune system damage. But the effects wouldn't stop there. The nitrogen dioxide created in the upper atmosphere would absorb visible light, creating a brownish haze that would dim the sky and reduce the amount of sunlight reaching the surface. This could trigger global cooling, a cosmic winter that could last for years or even decades. And when the nitrogen compounds eventually rained out of the atmosphere, they would form nitric acid, producing acid rain that would further stress terrestrial and aquatic ecosystems. This isn't pure speculation. Some researchers have proposed that exactly this scenario played out 440 million years ago, during the late Ordovician mass extinction, one of the 5 great mass extinctions in Earth's history. This extinction wiped out roughly 85% of marine species and occurred during a period of rapid global cooling that has never been fully explained by other mechanisms. In 2004, a team led by Adrian Melott of the University of Kansas published a paper arguing that a gamma ray burst within our galaxy could account for many of the peculiar features of the Ordovician extinction. They noted that surface-dwelling organisms, those near the top of the water column, were disproportionately affected compared to deep-water species, a pattern consistent with increased UV radiation from above. Burrowing species fared better than those living on the seafloor surface, again, consistent with the idea that radiation from the sky was the primary killer. And the rapid onset of glaciation that marked the extinction could be explained by the nitrogen oxide-induced cooling. Now, to be clear, this is still a hypothesis, not an established fact. Other explanations for the Ordovician extinction exist, including changes in ocean circulation and volcanic activity, but the GRB hypothesis remains compelling and has not been ruled out. Estimates suggest that a dangerously close gamma ray burst should occur about 2 or more times per billion years in our galaxy. Over Earth's 4.5 billion year history, the odds are reasonably good that at least one has happened close enough to do significant damage. And there's even a candidate progenitor right in our cosmic neighborhood, WR104, a Wolf-Rayet binary star system about 8,000 light-years from Earth, consists of a massive Wolf-Rayet star that will eventually die as a supernova. If it's spinning fast enough, it could potentially produce a gamma ray burst. And observations of the beautiful pinwheel-shaped dust nebula surrounding the system suggest that its rotational axis may be pointed roughly in Earth's direction, though more recent spectroscopic measurements suggest the angle may be larger and therefore less threatening. Should we worry? Well, probably not about WR104 specifically. The probability of it producing a gamma ray burst is estimated at around 1%, and the angle may not be quite right. And even if it did, 8,000 light-years is far enough that the effects, while serious, probably wouldn't be extinction level, but the broader point stands. Gamma ray bursts are real threats, and they've likely affected life on Earth before. It's humbling to think that the course of evolution on our planet may have been shaped, at least in part, by explosions in distant corners of our own galaxy. While the destructive potential of gamma ray bursts is sobering, they also serve as powerful tools for understanding the cosmos. Because they are so phenomenally luminous, They can be detected at enormous distances, serving as cosmic flashlights that illuminate the universe across more than 13 billion years of cosmic history. The most distant gamma ray burst ever detected, GRB 90,423, occurred at a redshift of 8.2, meaning its light traveled approximately 13 billion years to reach us. When this burst exploded, the universe was only about 630 million years old, less than 5% of its current age. Stars and galaxies were just beginning to form from the primordial gas left over from the Big Bang. By detecting gamma ray bursts at these extreme distances, astronomers can probe the conditions of the early universe in a way that few other observations allow. As the light from a distant gamma ray burst travels toward Earth, it passes through intervening gas clouds, galaxies, and the intergalactic medium. Each of these leaves its mark on the light in the form of absorption lines in the afterglow spectrum. By studying these absorption features, astronomers can determine the chemical composition, temperature, and density of the gas along the line of sight, essentially taking a census of the matter between us and the burst. This technique has been used to study the distribution of metals in the early universe, to probe the reionization epoch, when the first stars and galaxies ionized the intergalactic hydrogen, and to measure the rate at which the universe is expanding. Gamma ray bursts have also contributed to one of the hottest topics in modern cosmology: the Hubble tension. The multi-messenger detection of G 170,817, the neutron-star merger observed in both gravitational waves and electromagnetic radiation, provided an independent measurement of the Hubble constant, the rate at which the universe is expanding. While the uncertainty on that single measurement was large, future neutron-star merger detections with associated short gamma ray bursts are expected to refine this measurement significantly, potentially helping to resolve the disagreement between different methods of measuring cosmic expansion. And then there are the surprises that keep gamma ray burst researchers up at night, the events that don't fit neatly into the standard categories. In December 2022, astronomers reported GRB 211,211A, which lasted 51 seconds, well into long burst territory, and yet showed evidence of a kilonova, the hallmark of a neutron-star merger. This was followed by similar events like GRB 230,307A. These long-short bursts suggest that the simple 2-second dividing line between merger-driven and collapsor-driven bursts is more of a guideline than a rule, and that the universe is more creative in its destruction than we had imagined. The future of gamma ray burst science looks bright, if you'll pardon the pun. New and upcoming missions like the Space Variable Objects Monitor, launched in 2024 by China and France, the Cherenkov Telescope Array Observatory, now under construction, and potential next-generation gravitational wave detectors will allow us to observe gamma ray bursts with unprecedented sensitivity and across more of the electromagnetic spectrum than ever before. Each new event is a natural experiment conducted at energies and under conditions that no laboratory on Earth could ever reproduce. There is something almost poetic about using the most destructive events in the cosmos as precision measurement tools, but that is precisely what astronomers have learned to do with gamma ray bursts. Because gamma ray bursts are so absurdly luminous, they can be seen across truly staggering distances. And at those distances, the light from a burst carries information not just about the explosion itself, but about everything it passed through on its way to us. The intergalactic medium, the gas between galaxies, the dust within intervening galaxies, all of it leaves an imprint on the afterglow spectrum. In this sense, every gamma ray burst is a cosmic flashlight, briefly illuminating a random line of sight through the universe and allowing us to take a snapshot of conditions along that path. One of the most scientifically valuable applications of this technique involves studying the Lyman alpha forest. Hydrogen, the simplest and most abundant element in the universe, absorbs ultraviolet light at a very specific wavelength, 121.6 nanometers, known as the Lyman alpha line. As the afterglow light from a distant gamma ray burst travels toward us, it passes through numerous clouds of intergalactic hydrogen. Each cloud absorbs a bit of light at the Lyman alpha wavelength. But because the universe is expanding, each successive cloud is at a slightly different redshift. So each absorption line appears at a slightly different observed wavelength. The result is a forest of narrow absorption lines in the afterglow spectrum, each one corresponding to a different hydrogen cloud at a different distance along the line of sight. By analyzing this Lyman alpha forest in gamma ray burst afterglows, astronomers can map the distribution of hydrogen gas in the universe at different epochs. This is especially powerful at high redshifts, where the universe was much younger, and the gas distribution was very different from what we see today. Gamma ray bursts provide some of the most detailed probes of this early intergalactic medium, because their afterglows are, for a brief time, much brighter than the background quasars traditionally used for this kind of study. There's another measurement that gamma ray bursts have contributed to, one that has become one of the most contentious debates in modern cosmology: the Hubble constant. This number, which describes how fast the universe is currently expanding, has been measured by several independent methods, and the results don't quite agree. Measurements based on the cosmic microwave background, the afterglow of the Big Bang itself, give a value of about 67.4 kilometers per second per megaparsec. Measurements based on nearby supernovae and Cepheid variable stars give a higher value, around 73. This discrepancy, known as the Hubble tension, is either a systematic error in one or both methods, or a sign of genuinely new physics. Gamma ray bursts offer a potential way to resolve this tension. The multi-messenger detection of G170,817, the neutron star merger observed in both gravitational waves and electromagnetic radiation in August 2017, provided a completely independent measurement of the Hubble constant. The gravitational wave signal gives the distance directly, without needing to rely on the traditional cosmic distance ladder. The electromagnetic counterpart, including the short gamma ray burst, gives the redshift. Combining the two yields the expansion rate. The initial measurement from G170,817 had large uncertainties, giving a value consistent with both camps. But as gravitational wave detectors improve and more neutron star mergers with electromagnetic counterparts are detected, the precision will increase. Some projections suggest that within the next decade, multi-messenger observations of short gamma-ray bursts and kilonovae could narrow the Hubble constant measurement to within 2%, potentially settling the debate once and for all. And so these brief flashes of destruction, lasting seconds or minutes before fading into darkness, turn out to be among the most versatile tools in the astronomer's kit. They illuminate the distant universe, trace the history of star formation, probe the chemistry of intergalactic gas, measure the expansion rate of the cosmos, and test fundamental physics in conditions no laboratory could ever recreate. The universe may be violent, but its violence, it turns out, is extraordinarily informative. As we look to the future of gamma-ray burst science, several exciting developments are on the horizon. The James Webb Space Telescope, already revolutionizing our understanding of the early universe, has the sensitivity to observe the infrared afterglows and host galaxies of the most distant gamma-ray bursts. It may detect bursts from the epoch of reionization, when the first stars and galaxies were forming, providing unprecedented insights into the conditions of the early cosmos. The Cherenkov Telescope Array Observatory, currently under construction with sites in both the northern and southern hemispheres, will be far more sensitive to very high-energy gamma rays than current instruments. It will allow routine detection of the highest energy emission from gamma-ray bursts, opening a new window on the physics of relativistic jets and particle acceleration. Future gravitational wave detectors, including the proposed Einstein telescope in Europe and Cosmic Explorer in the United States, will be capable of detecting neutron star mergers at much greater distances than current instruments, combined with gamma-ray and electromagnetic follow-up. These observations will dramatically increase the number of multi-messenger events, providing a rich statistical sample for studying the physics of neutron star mergers and short gamma-ray bursts. And then there's the possibility that gamma-ray bursts may teach us something entirely unexpected. Throughout the history of this field, from the accidental discovery by the Vela satellites to the astonishing multi-messenger detection of G170,817, the biggest advances have been surprises, things nobody predicted, things that didn't fit the existing models. If history is any guide, the most exciting discovery in gamma-ray burst science is one that nobody has thought of yet. The universe, after all, has a habit of being more creative than we are. There's also SVOM, the Space Variable Objects Monitor, a joint mission between the Chinese and French space agencies that launched in June 2024. It carries both a coated mask gamma-ray imager and a soft X-ray telescope designed to rapidly localize gamma-ray bursts and begin follow-up observations within minutes. What makes SVOM particularly interesting is its focus on detecting high redshift bursts, those that occurred when the universe was very young. By alerting ground-based telescopes around the world within seconds of a detection, SVOM aims to catch the afterglows of the most distant gamma-ray bursts before they fade, allowing spectroscopic measurements that can probe the intergalactic medium at epochs that are otherwise almost impossible to study. And we shouldn't forget about the role of artificial intelligence and machine learning in the future of this field. As the volume of data from gamma-ray satellites, gravitational wave detectors, and optical survey telescopes continues to grow, the ability to rapidly classify, prioritize, and analyze transient events becomes increasingly important. Already, machine learning algorithms are being used to classify gamma-ray bursts in real time, distinguishing genuine cosmic events from instrumental noise and other sources of confusion. In the future, these tools may be able to identify subtle patterns in burst properties that human researchers have missed, potentially revealing new subclasses of gamma-ray bursts or unexpected correlations that could point toward new physics. The field has come an impossibly long way from those first confused signals picked up by nuclear test monitoring satellites in the late 1960s. What started as a military secret became the greatest unsolved mystery in astrophysics, and then one of the most dynamic, rapidly evolving fields in all of science. And the journey is far from over. We've traveled a long way in this story, from the suspicious blips on Cold War satellite monitors to the brightest explosion in recorded human history, from the confusion of hundreds of theories to the elegant clarity of collapsing stars and merging neutron stars, from the mystery of how gold is made to the unsettling possibility that a gamma-ray burst once reshaped life on Earth. And yet, in many ways, we're still at the beginning. We still don't fully understand the mechanism that produces the prompt gamma-ray emission. We don't know the precise conditions that determine whether a dying star produces a gamma-ray burst or just a regular supernova. We can't explain why the boat was so much brighter than everything that came before it. We're still wrestling with the strange hybrid events that blur the line between long and short bursts. But maybe that's the beauty of it. Gamma-ray bursts remind us that the universe is wilder, more violent, and more creative than we tend to assume. We look up at a quiet, star-filled sky and see serenity. But that calm is an illusion of distance. Out there, right now, somewhere beyond the reach of our eyes, a star is dying in a blaze that would outshine an entire galaxy. Somewhere, two neutron stars are spiraling toward each other, their dance growing faster, the gravitational waves growing stronger, the final collision just moments away. Somewhere, a jet of material is punching through the collapsing envelope of a doomed giant, about to break free and announce itself to the cosmos with a flash of gamma rays visible from the edge of the observable universe. These events don't concern us. They don't know we exist. They have been happening since before the Earth formed, before our sun ignited, before the Milky Way assembled its graceful spiral arms from the chaotic merger of smaller galaxies. They are part of the fundamental machinery of the cosmos, the processes that create the elements, scatter them through space, and set the stage for new generations of stars and planets. And sometimes, life, the gold in your ring, the platinum in your catalytic converter, the iodine in your thyroid. All of it was forged in the aftermath of catastrophic explosions, some of which lit up the sky with gamma-ray bursts that were briefly brighter than everything else in the universe. We are, in the most literal sense, the children of the most violent events the cosmos has ever produced. And the next time you look up at the night sky, remember, it only looks peaceful underneath that silence. The universe is always burning. Somewhere out there, right at this very moment, a gamma ray burst is going off. A jet of material accelerated to 99.99% of the speed of light is tearing through the collapsing envelope of a dead star. Or two neutron stars are finally meeting after billions of years of spiraling closer and closer. The light from that explosion is already on its way toward us, racing across the expanding void. It might arrive tomorrow. It might arrive in 1,000,000 years. It might never reach us at all. Its beam pointed harmlessly into empty space, witnessed by nobody. But it happened. It's happening right now. And it will keep happening long after our sun has exhausted its fuel, long after the Earth has gone dark, long after the last star in the Milky Way has flickered out. The universe doesn't need an audience for its grandest performances. It simply performs. And for as long as we're here, for as long as we have satellites in orbit and telescopes pointed at the sky and curious minds asking questions, we get to watch. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time.